I welcome you back in this afternoon lesson. It's Mr. Hyper taking you through, and this afternoon we are going to look at the phase diagrams for carbon dioxide and sulfur. And let's begin with the phase diagram for carbon dioxide. Phase diagram for carbon dioxide system. For carbon dioxide system. So here we are going to have okay, we were saying that we are going to look at the carbon dioxide system, the phase diagram for the carbon dioxide system, and also the sulfur system. But let's begin with the carbon dioxide system. So here we are going to have two axes. The first axis shows the vapor pressure, and this is vapor pressure in atmospheres. And here we are going to have the temperature. Now, having this here, I'll have my point and my line. This is a straight line. Draw it as a straight line. This is my point. Let me call this one my point O, and let me call this one my point A. Then here, I'm calling this one my point B, and I'm calling this one my point C. Right? So this is solid, this is liquid, and this is the gas. I'm going to bring in some imaginary lines. The first imaginary line is from Z up to Y, and then also X here. So we are going to look at how this phase diagram differ from, how does it differ from the one of water, and we are going to look at the presentation or what these lines or curves represent. So as I've told you, these two are different simply because of what we are going to look at. Now, like water, also carbon dioxide can exist as a liquid, solid, or as a gas. However, one may not easily recognize the liquid part due to different reasons, but we are going to look at how possible it is. But before I take you to that system, I want to first show you how different this system is from the one of water. But to show you the difference it has from that of water, maybe we have to redraw that of water somewhere so that we compare easily. Then we interpret the one of carbon dioxide separately. Now, the one of water, we add it like this, where here we had a line, we had a curve, and here was an imaginary curve. So we're like, this is A, this is O, this is B, and this is C, and this is D. That is from the previous video. Now, of course, well, like this is 100. Remember here we had put 1.0. Of course, temperature in degrees Celsius, and of course here pressure, vapor pressure in atmospheres. Now, these two are different in that for this case, line OA slopes away, line OA slopes away from the vapor pressure axis. While here, it is coming to the vapor pressure axis. But here, for carbon dioxide, line OA slopes away. You see the distance, even if you compare the distance, you can see that the distance here is quite bigger compared to this. So for carbon dioxide system, this line OA slopes away from the vapor pressure axis, indicating that one indicates that the melting point of solid carbon dioxide increases with an increase in pressure. If it slopes away from the pressure axis, then to me that an increase in vapor pressure increases the melting point of solid carbon dioxide. All right, so if we are to compare that two, we can easily say that line OA for carbon dioxide slopes away from vapor pressure axis, indicating that the melting point of carbon dioxide, all right, of solid carbon dioxide, let's say, of solid carbon dioxide increases with the increase in pressure, Reason being, the molecules of carbon dioxide in solid phase are packed more closely than in liquid phase, unlike in water. So in solid phase, actually, we can give the reason. This is because the molecules of carbon dioxide in solid phase are closely packed together, okay, are closely packed together than in the liquid phase, which is unlike in water. So meaning that in water it is vice versa. But for solid carbon dioxide, the particles are closely packed together, and therefore, for you to break the forces of attraction between the particles of carbon dioxide, you have to increase the pressure. Then another difference is that the triple point of carbon dioxide occurs at a higher vapor pressure than that of water. For water, you can see that the vapor pressure, the triple point is here. So the vapor pressure is here. And for this case, the vapor pressure is higher at triple point. So comparable, or on comparison, when you're looking at the vapor pressure at which triple point occurs and the vapor pressure at which triple point occurs here, for carbon dioxide, the triple point occurs at a higher vapor pressure than that of water. Remember, we said that triple point is that point where all the three phases coexist in equilibrium. All right. Now, another thing which we need to note that at point X, a system at point X is in a solid phase. At this point X, it is in a solid phase, as you can see. It is in a solid phase and changes to vapor along XY. It changes to vapor, or what you call the gas, along XY. So we have to note those points here. At X, the system is in solid phase and changes to vapor phase along XY when heated at reduced pressure. In other words, sublimation takes place along XY, meaning that this along XY we have sublimation, whereby the solid is going to the gas. But at point Y, the system is in vapor phase. At this point Y, the system is in vapor phase. What does it mean? It means that when compressed at constant temperature, it changes to liquid along YZ. So when you compress this gas, when you compress the system at gaseous phase or in gaseous phase, when you compress it, okay, at constant temperature, it changes to liquid along YZ. So when compressed, okay, when compressed at constant temperature, it changes to liquid along YZ. Additionally, point O is a triple point. You need to note that O I'm adding here, O is a triple point, O is a triple point for carbon dioxide, meaning that at this point, all the phases coexist in equilibrium, okay? And this point is greater than 1 atmosphere. At this point is greater than 1 atmosphere, implying that solid carbon dioxide boils without passing through the liquid state. So at this point, at the triple point here, is beyond 1 atmosphere, okay? Implying that solid carbon dioxide does not pass through the liquid phase to change to vapor. In other words, it just sublimes. So that is all about the carbon dioxide. That's all about the carbon dioxide. And we can also look at the reason as to why this line OA slopes to the right. Of course, we have already talked about it, that it's because the melting point of solid carbon dioxide increases as the pressure also increases. So that is it all we can talk about the phase diagram for carbon dioxide. Let's now look at the sulfur system. Let's look at the sulfur system. Sulfur system. The sulfur system. Well, when you talk about sulfur, what you should remember in your head should be the fact that sulfur exhibits allotropy. From our O level, we looked at what allotropy is. Okay, so here we are saying that sulfur exists as, okay, sulfur is allotropic. It is the same element, but it exists in different forms. And those different forms we are concerned in here are 2 forms. And the sulfur forms we are going to talk about basically is the rhombic sulfur. We've got rhombic sulfur, and that rhombic sulfur, one can call it alpha sulfur. Then we've got what we call monoclinic sulfur. Monoclinic sulfur, which we can call the beta sulfur. So we are having those two forms of sulfur, and we shall need to know that at ordinary temperatures, the stable allotrope is rhombic. Okay, so this is stable at ordinary temperatures. That is the most stable form of sulfur. Now, the temperature at which these two allotropes are in equilibrium, that very temperature where we have rhombic sulfur and monoclinic sulfur existing in equilibrium is what we call the transition temperature. So the transition temperature refers to that temperature at which the two allotropes of sulfur are in equilibrium, and that temperature is 96 degrees Celsius. Now, you need to know that when rhombic sulfur is gently heated, when you heat rhombic sulfur, it is converted to monoclinic sulfur at this temperature, because we say that at this temperature, they're in equilibrium with each other, meaning that if at ordinary temperatures we have rhombic, is at ordinary, meaning that when we heat it up to 96 degrees Celsius, it is going to be converted to monoclinic. Now, this further heating results into this monoclinic sulfur changing to liquid sulfur. Now, this further heating at a temperature of 119 degrees Celsius will change this monoclinic sulfur to liquid sulfur. So that is simply the mechanism that that occurs, or the route that sulfur goes through once heated. Rhombic sulfur is stable at ordinary temperatures, but once heated, converts to monoclinic, which continuously, when heated, converts to the liquid sulfur. So we are going to look at the summary of the diagram of the sulfur system, and we interpret it together. We see how these can be also explained. So let's draw this phase diagram of sulfur and see how we can talk about it. So this is pressure in atmospheres, and this is temperature. Allow me to use abbreviations, but write full statements. Now we shall have a point here. Shall have a point here. This is a straight line. Then we shall have a curve. And we shall also have another curve. So at this point, let me call this one point C, and let me call this one point D. Then let me draw a line and continuously project it. So at this point, let me call this one E, and let me call this one point F. Then let me project it further. It's a curve, not a line, it's a curve. And let me call this one my point A, then this one my point B. So I have A, B, C, D, E, F. All right. Then, of course, I have to label it. Let me call this one my liquid phase. Let me call this one my vapor phase. Let me call this one my solid phase. This is what we call rhombic sulfur. This is rhombic sulfur. And still in this region, we are still having a solid state. But when rhombic has been converted to monoclinic sulfur, so this is monoclinic sulfur. All right, so here we shall have imaginary lines, which I will explain. So I'm going to call this one point X, I call this one point Y, and I call this one point Z. Now, we are going to talk about each curve and what it represents, all right? Now, curve AB, we are going to begin with the curve AB. That curve AB is the sublimation curve of rhombic sulfur. Sublimation curve of rhombic sulfur. Whereby it shows the variation of vapor pressure of rhombic sulfur with the temperature. Shows variation of vapor pressure of rhombic sulfur with the temperature. That is curve AB. Then we've got curve BC. Now with BC, we have already gone into another sulfur, but solid, then vapor. So still it is solid to vapor. So still it is sublimation curve, but not for rhombic, but instead for monoclinic sulfur. So curve BC shows the sublimation curve of monoclinic sulfur. And then when we talk about CD, this is vapor, liquid, so we shall call it vaporization curve. One can call it vapor pressure curve of liquid sulfur, because we're having the equilibrium between liquid and vapor, so liquid sulfur. And with this point, it will show the variation of vapor pressure, shows variation of vapor pressure of liquid sulfur with the temperature. All right. Then we go ahead. That was, now we can go to BE. BE, this BE is what we call the transition curve. Transition curve. BE is a transition curve. And what happens on the transition curve? It shows the effect of pressure. All right. It shows the effect of pressure on the transition temperature being 96 degrees Celsius. So it shows the effect of pressure on the transition temperature between rhombic sulfur and monoclinic sulfur. And along this line, monoclinic sulfur is in equilibrium with the rhombic sulfur. So you can note that, it can be noted that it shows the effect of pressure on transition temperature. And we say that along this line, rhombic sulfur and monoclinic sulfur are in equilibrium. So that is also another point to note or to mark there. Then we've gotten what we call CE, point CE. CE. This point CE is what we call the fusion curve. It is the fusion curve for monoclinic sulfur. Fusion curve for monoclinic sulfur. And what does it show? It shows the effect of pressure still. It shows the effect of pressure on melting point of monoclinic sulfur. Shows effect of pressure on melting point of monoclinic sulfur. All those statements I'm mentioning are marking points. Only that I don't want to turn to another side when the diagram is on this page, but all the statements I add after talking about the name of the curve, all the statements I add will deserve you a mark. Then we have got curve EF. Curve EF. Curve EF is the fusion curve for rhombic sulfur. This one is the fusion curve for monoclinic sulfur, but this one is the fusion curve for rhombic sulfur. So EF is the fusion curve for rhombic sulfur. Then we have point B. Now that point B is very, 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 very major. Point B is now our triple point. Our triple point is at point B. So this triple point is for rhombic sulfur, all right, monoclinic sulfur, and vapor sulfur. Rhombic, monoclinic, and at the same rhombic, monoclinic, and vapor. So this point B brings all these three in equilibrium: solid, monoclinic, and then the vapor. So point B, the triple point, so we shall have different triple points here. The first triple point is point B, where we have rhombic, where we have monoclinic, and vapor sulfur existing in equilibrium. Then also we have got point C. Point C is another triple point. So point C is a triple point of which ones? Point C is a triple point for monoclinic. You see, we have monoclinic, all right? We have liquid sulfur and still vapor. So here, point C is a triple point of monoclinic sulfur, vapor sulfur, and liquid sulfur. Then we've also gotten point E. Point E is also a triple point here. Point E is a triple point for rhombic, triple point for rhombic. Okay, we have for rhombic, this side, rhombic, monoclinic, and liquid sulfur. Rhombic, monoclinic, and liquid sulfur. Then our last point is point D, where point D is our critical point. Point B is our critical point, and critical point, we defined it as the point or that very point beyond which liquefaction does not take place, however much pressure is exerted. So however much you increase pressure, to what extent, beyond point D, we don't have any liquefaction of sulfur. So that is the summary of the phase diagram for sulfur. These triple points, you have to look at them very wisely. We say that at B, it is the rhombic, it is the vapor, and the monoclinic sulfur that are in equilibrium. At point C, it is the monoclinic, the liquid, and the vapor that are in equilibrium. But at E is a triple point. Triple, it means that there must be 3 phases in equilibrium. So at E, it is the rhombic, monoclinic, and the liquid sulfur that exist in equilibrium. And this point D of ours, you defined it as the critical point beyond which no liquefaction of sulfur takes place, however much pressure is increased. Then, let's talk about these imaginary lines. What do they mean? Now, when any phase is subjected to change in temperature and pressure, it will disappear and another dominates. What do I mean? When any of these phases is subjected to change in pressure and temperature, or when you change the pressure and temperature of these other phases, it means that one of the phases, that phase that has been subjected to those physical conditions, it will disappear and another one dominates. For example, rhombic sulfur at X. When you look at rhombic sulfur at X, when heated at reduced pressure along XY, when you heat rhombic sulfur along XY, what happens? It changes to monoclinic sulfur before turning into vapor. It first changes to monoclinic sulfur, then it turns to vapor. Meaning that it has changed from rhombic and monoclinic as it dominated, then it continues up to when it goes to vapor stage. Okay, then at the point Y, that is in vapor state, when you compress at constant temperature, it changes to liquid sulfur along YZ. So simply, that is what I can talk about the system of the sulfur system. So it has been a nice interaction. Till next time, we are going to look at 2 component systems, whereby under this we're going to look at the eutectic mixtures. We are going to look at the miscible liquid mixtures, partially miscible liquid mixtures, immiscible liquid mixtures. But amazingly, all these aspects we're going to look at are very, very essential in our daily life, and they are applied within our daily life to work on our lives. So till next time, remain hyper, keep subscribing to us. Let's meet in the topic or in the subtopic of this topic as eutectic mixture. See you then.